Hello, everyone. Welcome to our Deep Dive podcast, where today we'll be reviewing the paper, Turning Whisper into Real-Time Transcription System. Are you ready to explore how Whisper, a state-of-the-art speech recognition model, was adapted for real-time use?
Absolutely. I'm excited to discuss this. Whisper has been making waves in the speech recognition community, but as the authors point out, it wasn't originally designed for real-time transcription. That's a big limitation for live applications, isn't it?
Yes, it is. The original Whisper model, developed by OpenAI, is excellent for offline processing. It can transcribe and translate speech in nearly 100 languages, but it expects the entire audio file to be available before it starts processing. That's not ideal for live events or meetings.
Right. So, the main contribution of this paper is Whisper streaming, which enables real-time transcription and translation using Whisper-like models. The authors implemented a streaming policy called LocalAgreement to make this possible. Can you explain what LocalAgreement is?
Sure. LocalAgreement is a streaming policy that helps decide when to output parts of the transcription as confirmed. It works by comparing the outputs of the model on consecutive audio chunks and finding the longest common prefix. This way, only the stable, agreed-upon part of the transcription is emitted, reducing errors from premature output.
That's clever. So, instead of waiting for the whole sentence or document, the system can output parts of the transcription as soon as they're stable. This reduces latency, which is crucial for real-time applications like live captioning.
Exactly. The authors used LocalAgreement too, meaning they compare the outputs from two consecutive updates. If the same words appear at the start of both outputs, those words are considered stable and are emitted as confirmed output.
I see. But how does the system handle the audio input? Does it process the audio in fixed-size chunks?
Good question. The system uses an audio buffer, which accumulates incoming audio. The parameter min chunk size controls the minimum duration of audio processed in each iteration. If processing takes longer than min chunk size, the next update is triggered immediately with the accumulated audio.
That makes sense. So, min chunk size is a trade-off between latency and quality. Smaller chunks mean lower latency but potentially less context for the model, which could hurt quality.
Precisely. The authors experimented with different chunk sizes to find the optimal balance. They also used a re-implementation of Whisper called Faster Whisper, which is about 4 times faster than the original, thanks to the C-Translate 2 inference engine.
That's a significant speed-up. Now, let's talk about the update loop. Each time a new audio chunk arrives, the system processes the entire buffer with Whisper, applies the LocalAgreement policy, and updates the confirmed output. Is that correct?
Yes, that's the core of the update loop. The buffer always starts with a new sentence to maintain Whisper's high quality. After each update, the system saves the timestamp of the last confirmed word and trims the buffer accordingly.
Interesting. What about handling already confirmed output? How does the system avoid reprocessing or duplicating words?
The system skips the confirmed part by comparing the timestamps and n-grams of the new output with the last confirmed output. If they match, those words are skipped. This helps avoid unnecessary repetition and keeps the output clean.
That's efficient. The authors also mention trimming the audio buffer to avoid long latency spikes. They use sentence-ending punctuation as a cue to trim the buffer, ensuring it doesn't exceed about 30 seconds.
Correct. They also use a language-specific sentence segmentation tool to make sure the buffer always contains a single sentence. If the buffer gets too long, they keep only the last confirmed segment.
Another interesting feature is the use of the prompt parameter in Whisper. By extracting the last 200 words from previous confirmed output, they provide context for the model, helping maintain consistency in style and terminology.
Yes, that's important for long-form transcription, where context matters. The system also has an option to activate or deactivate Whisper's built-in voice activity detection, or VAD. This impacts both quality and latency.
Speaking of VAD, the authors conducted experiments to see how it affects performance. For English original speech, which is fluent and has few pauses, they found that turning off VAD reduced latency without hurting quality.
That's right. For simultaneous interpreting, like German and Czech, which have more pauses, Activating VAD improved quality by filtering out silence and non-voice sounds with only a small increase in latency.
Let's look at the evaluation setup. The authors used the ESIC corpus, which contains manually transcribed speeches from the European Parliament in English, German, and Czech. They measured word error rate, WER, and latency.
Yes, WER is the standard metric for ASR quality, calculated after removing punctuation and casing. Latency is measured as the time difference between when the ASR emits a word and when the corresponding gold word was spoken.
They ran simulations on NVIDIA A40 and L40 GPUs, sometimes with other processes running on the same machine. This makes their evaluation realistic, since in practice servers are often shared.
Exactly. They found that WER had low standard deviation, but latency varied more due to unpredictable computation conditions. To account for this, they ran each setup 10 times and reported mean and standard deviation.
Now, let's discuss the results. With 1 second min chunk size, the average latency was 3.3 seconds for English, 4.4 seconds for German, and 4.8 seconds for Czech. WER was about 2% higher than offline mode for English and German, and 6% higher for Czech.
That's impressive for real-time processing. The higher WER and latency for Czech are likely due to less training data and greater morphological complexity. Larger chunk sizes increased latency but improved quality, as the model had more context.
The authors also compared streaming mode to offline mode and a computationally unaware simulation where processing time is assumed to be 0. This helps separate the impact of model uncertainty from hardware limitations.
Yes, in the computationally unaware setup, latency was about twice the chunk size, as expected with LocalAgreement 2. The actual latency in practice was higher due to computation time.
The authors demonstrated Whisper streaming at a real multilingual conference, integrating it with the LocalAgreement framework. They ran 5 parallel Whisper streaming workers for ASR and speech translation in English, Czech, and Ukrainian.
A human operator monitored the outputs and could redirect streams as needed. The qualitative evaluation showed that Whisper streaming was robust and reliable, with acceptable latency and high quality, even for long-form speech.
They also created a demonstration video showing real-time outputs for English, German, and Czech compared to gold transcripts. This helps visualize the latency and errors.
That's a great way to showcase the system's capabilities. The authors plan to demonstrate it at the IJC NLP-AACL 2023 conference, allowing participants to try it in any of the 97 languages supported by Whisper.
Now, let's discuss some limitations. The ESIC corpus was created some time ago, so there's a risk that some data leaked into Whisper's training set, potentially biasing the evaluation.
Yes, and the performance on more affordable hardware hasn't been tested yet. The reported latency and quality may not generalize to other languages or language variants, especially those with less training data.
The focus of this work was on demonstrating online capabilities, not optimizing the algorithm or implementation. Actual latency may fluctuate, and the reported average doesn't provide an upper bound.
To guarantee maximum latency, the streaming policy would need modifications, possibly at the cost of quality. Also, the authors haven't compared Whisper streaming to other state-of-the-art systems, as a common evaluation framework is still pending.
Despite these limitations, Whisper streaming is a significant step forward in making powerful ASR models usable for real-time applications. The open-source release and demonstration video make it accessible to researchers and engineers.
Absolutely. The integration with LocalAgreement and successful deployment at a live conference show its practical usability. The system's robustness and adaptability are impressive.
Let's talk a bit more about the technical details. The use of LocalAgreement 2 is key to balancing latency and quality. By requiring agreement between 2 consecutive outputs, the system avoids premature emission of unstable words.
Yes, and the choice of min chunk size is crucial. Smaller chunks reduce latency but may hurt quality, while larger chunks improve quality at the cost of higher latency. The authors provide detailed results for different chunk sizes.
For English, with 1 second chunks, WER was 8.1% and latency was 3.62 seconds. For German, WER was 9.4% and latency was 4.37 seconds. For Czech, WER was 12.9% and latency was 4.76 seconds.
The offline WERs were lower, as expected, since the model has access to the entire context. For English, offline WER was 7.9%, for German 9.2%, and for Czech 12.3%.
The difference between streaming and offline WER is relatively small, especially for English and German. This shows that the streaming policy is effective at maintaining quality.
The authors also analyzed the impact of VAD. For English, turning off VAD reduced latency by about 0.23 to VAT 0.41 seconds, with negligible impact on WER. For German, turning on VAD improved VAD by turning on VAD improved VAD by The different administration varnana, very was choosing VAD the comprehensive was a great class sort of the authors in Agit Viner don't see nothing the nutshell very sick pictures the Gunstein with the 1 second chunk system painting the seed they can't the authors also analyzed the impact of VAD. For English, turning off VAD reduced latency by about 0.23 to VAT 0.41 seconds, with negligible impact on WER. For German, turning on VAD improved VAD by turning on VAD improved VAD by with only a small increase in latency.
That's a useful insight for practitioners. Depending on the language and type of speech, VAD can be tuned to optimize performance.
Another interesting point is the use of the prompt parameter to maintain inter-sentence context. By providing the last 200 words of confirmed output, the model can produce more consistent and coherent transcriptions.
That's especially important for long-form transcription, where context and consistency matter. The system also trims the buffer at sentence boundaries to avoid excessive latency.
The authors mention that the buffer is limited to about 30 seconds. If the confirmed output includes a sentence-ending punctuation mark, the buffer is trimmed at that point.
This helps keep latency under control and ensures that the model always processes manageable chunks of audio.
The system is also designed to be flexible. While the authors used Whisper, the underlying model can be replaced with any speech-to-text or translation model that provides word-level timestamps and punctuation.
That's a valuable feature. As new models are developed, they can be plugged into the Whisper streaming framework.
The open-source release makes it easy for researchers and engineers to experiment with different models and settings.
The authors also discuss the importance of reproducibility. They ran each simulation 10 times to account for variability in latency due to shared hardware.
They found that WER was stable across runs, but latency varied more depending on system load. This highlights the challenges of real-time processing in shared environments.
For real-world deployment, it's important to be aware of these factors and design systems that can handle variability in computation time.
The authors recommend starting Whisper streaming shortly before the speech begins and turning on VAD to avoid missing the first words and to filter out non-voice sounds.
If reducing latency is critical, an adaptive protocol for toggling VAD on and off can be implemented.
The integration with ELECAR demonstrates the system's practical usability. ELECAR is a framework for distributed, multi-source, multi-target live speech transcription and translation.
Whisper streaming acts as a worker in the ELECAR system, providing real-time ASR or translation services. The outputs can be further processed, for example, by translation workers, and displayed as live captions.
At the Multilingual conference, the system handled 3 parallel language streams: Czech, English, and Ukrainian. Human interpreters provided simultaneous interpreting, and Whisper streaming transcribed and translated the speech in real time.
A human operator monitored the outputs and could redirect streams as needed. The qualitative evaluation showed that Whisper streaming was robust and reliable, with acceptable latency and high quality.
The demonstration video provides a visual comparison of real-time outputs and gold transcripts, highlighting latency and errors.
The authors plan to demonstrate the system at the IJCNLP-AACL 2023 conference, allowing participants to try it in any supported language.
In conclusion, Whisper streaming is a significant advancement in real-time speech recognition and translation. By adapting Whisper for streaming, the authors have made it usable for live applications.
The system achieves low latency and high quality, with flexible settings for different languages and types of speech. The open-source release and integration with LocalAgreement make it accessible and practical.
There are some limitations, such as potential data leakage in the evaluation corpus and untested performance on affordable hardware. The system's latency may fluctuate, and further optimization is possible.
Future work could include comparisons with other state-of-the-art systems, evaluation on more languages, and further optimization of the streaming policy.
Overall, this paper demonstrates how a powerful offline ASR model can be adapted for real-time use, opening up new possibilities for live transcription and translation.
That wraps up our review of turning Whisper into real-time transcription system. We hope you found this discussion informative and engaging.
Thank you for joining us. To summarize, the paper presents Whisper streaming, a real-time adaptation of Whisper, achieving low latency and high quality for live transcription and translation, with practical deployment in multilingual events.
Stay tuned for our next episode, where we'll review another exciting paper in the field of speech and language technology. Goodbye.
Goodbye, everyone.